Hello and welcome to the third lecture in 12th chapter of our comprehensive course on AI, machine learning and data science. Now, here we are slowly entering into this phase of data science life cycle, that is feature engineering. Because what happens is in exploratory data analysis, in its pure definition, we don't manipulate the data. Of course, we put some values instead of none and we remove some deduplication, etc. But we do not change the value of each and every row in any particular column. Only a few missing values or duplicates or outliers. So majority of the rows or majority of the observations in every column, around 95% observations are not even touched in this EDA. But once exploratory data analysis is done, now your data frame is free of null values, outliers, duplicate rows. Still, a few things need to be done. So ideally, here there should have been one more this kind of rectangle, which should have data pre-processing and then feature engineering. But it is okay because many books or data scientists include the term pre-processing as a part of feature engineering only. So now we want to talk about some such pre-processing. And in the pre-processing, we want to talk about normalization and standardization. So that also we have done in much detail earlier in 7th chapter. So this will be, here you can see that we created one data frame like this, and I explained in very much detail min-max scaling, normalization. By its definition, actually we learned. Then I told that there is no need to do every time things by its definition, but you can do things by standard scalar and scalar object of sklearn library. So somewhere here you will find that scalar object will be created, and we will use that scalar object for scaling. Okay, so maybe no, here it is just scaled data and unscaled data both are created manually, but later on we did but yes, this one maybe here sklearn pre-processing import standard scalar, and similarly from sklearn dot pre-processing import min-max scalar. Okay, then you create a scalar object and apply scalar dot fit transform to your data frame. Okay, to which columns, that also you can specify. If you want to apply only to specific columns, then you can do that, or if you want to apply to all the columns, then you can do that also. Okay, so here when you write columns is equal to df dot columns, that means apply to all the columns of my data frame. So we did a very detailed discussion of this normalization and standardization in chapter 7. So again, this is just a repetition of those things, but some things are so important that it is better to repeat them whenever they are again going to be required in next few chapters, rather than relying on students or learners' memory that they are doing everything. Okay, they will be able to retain everything. So techniques for data normalization and standardization. First of all, learn when normalization and standardization is required. So I give in that chapter this kind of example also, that maybe you have certain columns which are like this is still deduplication, just a minute. Yes, you have certain columns which are supposed like this. Okay, and you can see that income varies over a very large region. Okay, it is having values starting from 45,000 to 65,000, while age varies from 25 to 45 only, while education varies from 12 years of total education to 18 years of total education. So what happens if I use this data as it is? Then the scale of income is very large, and therefore it might, not it might, but it does have undue dominance. It does emerge as an undue dominant predictor of whatever you are predicting. Okay, so suppose there is one other thing based on this income you are predicting maybe savings. So then this income will become unduly dominant predictor of savings compared to others, because its scale is itself large. So if I want to build a real robust model, then I should bring all of them to same scale. So what we do is, first we drop this gender column because normalization and standardization that applies only to numeric column. Then these are my three columns now, numeric column, and we create this kind of min-max scalar. Instead of that, you can create now the same columns which were like this now have become like this. Now you can see what the change has occurred is now the minimum value is 0, maximum is 1. Here also minimum value is 0, maximum is 1, and here also minimum value is 0 and maximum is 1. So that means now all three columns have same scale. None of them is extremely high range, and none of them is very small range, that problem is solved. Okay, and you can, I showed you by plotting that actually even after doing this thing, that your data distribution does not change at all. This is the original income, 45,000 to 65,000, and this is the new income, 0 to 1. But see how beautifully that the scaling process, min max scaling, takes care that the original data distribution is not disturbed at all. Okay, so here also you can see that KDE plot also is identical before scaling and after scaling, right? So that we have done. Then instead of normalization, we can do standardization also. In standardization, what we do is, in normalization, what was our aim? The values should range between 0 to 1. In standardization, our aim is that all values, each column, each and every column should have mean equals to 0 and standard deviation equal to 1. Okay, so these are again the same columns. If I describe, then you can see the minimum value is here this and maximum value is this. So range is pretty large. Age has very moderate or little range, and education has even smaller range. Just total difference between max and minimum is 6. So apply this time. Somewhere I had shown the other type of scaling in which the data will change to that way, that the each column will have mean equals to 0 and standard deviation equals 1. So yes, this is that case. So you can see that mean is 2.2 into 10 raised to minus 17, that is 0.00016 zeros and then 222. Then the standard deviation is nearly 1.11. Here also mean is 6.66 into 10 raised to minus 17, that means 0.016 zeros and then 661. Okay, standard deviation is 1, and here the mean is 0 and the standard deviation is again 1. So this is which kind of scalar was used. If you check, then yeah, I think directly the previous scale data that was used here. Okay, so this data was used. That means standard scalar was used. So standard scalar is the scaling in which the data columns are values are changed in that manner so that the mean is nearly 0, not nearly, but it is exactly 0. This much value it shows because of the floating point calculation inaccuracy of our computer. And standard deviation is 1, mean is 0, standard deviation is 1. So this was the KDE of original data frame before applying standard scaling, and this is the KDE of scaled data frame. Mean is 0 and standard deviation is 1. So we did a lot of detailed discussion. So please refer to that chapter also. Now here I am just quickly revising. Normalization is this thing and standardization is this thing. When I say normalization is this thing, means what? That I am converting the column in such a manner. Here I am converting the column first in standardization. I am converting the column in such a manner that its mean value is 0 and standard deviation is 1. While here I am converting the values in such a manner that the minimum value is 0. You can see vertical axis starts from here, so the minimum value is 0 and the maximum value is 1. So all columns will be confined to range 0 to 1. Okay, while here there is no y-axis here, so this whole plot can be anywhere. So minimum and maximum value need not be 0 and 1, anything it can be, but their mean, arithmetic mean must be 0 and standard deviation must be 1. Okay, so that is the difference. Data normalization and standardization are crucial pre-processing steps in data science and especially in machine learning. The techniques help in scaling the data to a standard format, making it easier for the algorithm to process. Normalization converts the data over the range 0 to 1. However, there are some normalization techniques which prefer to convert over -1 to +1. So that is also fine. But in short, between a closed bound, all the observations are converted and without disturbing the data distribution, and therefore the scale of all columns would be similar. This is particularly useful for algorithms which are sensitive to the magnitude of input data. I gave the example of that income, etc. That before scaling, the values were ranging over 25 to 85,000, but after scaling, the values are ranging from just say -4 to +4. Fine. So that is, and second also -4 to +4, and so on. So all features will have same scale. Okay. Then standardization involves rescaling the data too. In standardization, we do not confine all the observations to some closed bound like this. Instead, we ensure that each and every column has value which are such that mean of them is 0. That means data is symmetrically distributed on either side of mean, so that every positive value is cancelled by every negative value. So when you find mean is nothing but sum of observations divided by number of observations. So when you do sum of observations, then the values will cancel each out, and therefore mean is 0 and standard deviation is 1. This process ensures that the data features contribute equally to the result. So here also, ultimately, it is same purpose and improves the algorithms convergence stability. Now that is important because many algorithms, in fact most data science algorithms, pass through the data set several times They are called iterations. So they will not find the solution immediately, but they will pass through the whole data set, say 50 times or 100 times or even 1000 times, depending upon you have to define n iter, a parameter for n underscore iter, number of iterations. So it passes through the whole data set several times and finds the most accurate version of the model using that algorithm. That process, when the most accurate version is found, or the error is minimized, or the accuracy is maximized, then we say that algorithm has converged. Now, if you don't do normalization or standardization first, then that conversion may occur after say 500 iterations. But if you feed the algorithm with standardized or normalized data, so at that time the same convergence may occur over 100 iterations. So it saves the time and even accuracy is also better. Okay. Now, as usual, we follow our standard method. We want to learn any concept, we create our synthetic data. So suppose this is the data dictionary. One is, these two columns are there, feature 1 and feature 2, and I'm using np.random.randint. So it will create a random integer observations between these two values, okay, and total 100 observations will be created. This will create normal distribution, np.random.normal, and it will create observations from 100 to 20. So this is the value which is at one higher end, and this is the value at the lower end, and again it will create 100 observations. So if I execute, I get this kind of data. Clearly here, there is not much difference between the scale, but still there is a difference between the scale. This is of the 2 digits, that is of the order of 100, while this is of the order of 1000. Okay, so if you want your algorithm to converge quickly and give accurate result, then you can use some scaling technique. Now, either you can use this line from sklearn.preprocessing import min max scalar, or you can use from sklearn.preprocessing import standard scalar. Okay, once that is done, rest of the steps are always same. Create a scalar object. If you have imported min max scalar, then create min max scalar object. If you have imported standard scalar, then create standard scalar object. And then next is apply. Don't look at this left side at present. Just apply that scalar object to your column on which you want to apply, to your entire data frame. So scalar.fit transform. Okay, so apply this scalar object to which columns? Then df feature 1 and feature 2. You can simply write df also in this case because it has only 2 features, but it is good to explicitly specify to which features you want to apply the scaling. And once that scaling is done, I don't want just to do the process temporarily. I want to change the values of my feature 1 and feature 2 in my original data frame. So assign that value. So now you can read the left side to columns df feature 1 and feature 2. So now my feature 1 and feature 2 normalized data would appear like this. The difference is clearly visible that the values are highly almost on the same scale. Okay, almost on the same scale. So min-max scalar rescales the data to 0 to 1 range, and this normalization is achieved by subtracting the minimum value of each feature and dividing the range of that feature. Now that explanation I had provided here in that 7th chapter. We started from scratch. Even we did not use sklearn or any library. We started from scratch. So each observation, these are the observation, we subtracted the mean value from that observation. Then I got xi minus x minimum, that is each observation minus the minimum of all observations. So minimum was 7, so I subtracted 7 from all observations. Then I divided by range. So range is what? The maximum value minus minimum value. So maximum value was somewhere 34 and the minimum value was 7. So 34 minus 7. So that is each of this, each value in this column was divided by 34 minus 7, or that is 27. These are called my min-max scaled values. So if you want to do everything manually, then this is how you do it. But now we have min-max scalar, and that did it for us, because manually here there were only few observations, so it is fine. But for many observations, it will not be good. And you can check the property of that min-max scaling. We did no, I think here we have scaled. So let me take this down. Okay, you can check the property of min-max scaling df.describe. So then you will see that all observations have minimum value 0, both features, and maximum value 1. So all are scaled between 0 and 1. So min-max scaling or normalization changes the observations in such a manner that every column has minimum value 0 and maximum value 1. It can also do -1 to 1 in certain cases, but here we have done 0 to 1. But it does not change the data distribution. As I said here, that the plot remains the same. This was before scaling, min-max scaling. This is after min-max scaling, but absolutely no difference. That is the beauty of this technique. Okay. Now, standardization. Standardization, as I said, is this technique here, in which we don't confine the data to some close bound like 0 to 1 or something. Instead, we symmetrically distribute the data points such that there are equal number of data points towards positive side of one value and equal number towards negative side of that value, so that the mean will obviously become zero, because mean is sum of observations divided by number of observations, but sum will also be itself be zero, right? And standard deviation of the data set should be exactly 1. So let us check that for which are we going to produce the data frame once again. Yeah, I think yes, we are going to produce the data frame once again, or we are going to use this same data frame. Yes, okay. Maybe better would be just for the sake of hmm, perfection, let me write this line of code once again and create the data frame once again and then apply standard scaling. So I'm creating the data frame. This is my original data frame, right? Now applying the standard scaling. So this time from sklearn pre-processing, I am importing standard scaler. Rest of the steps remain same. That create a standard scaler object and then don't look at left side, but always read the right side first. Then apply that scalar object. That means scalar dot fit underscore transform. Apply to what? Then apply to the df inside which you will supply a list of features. Okay, so that is subset of that subset of df containing your features where you want to apply it. Now here it will not make any difference because there are only two features, but sometimes if there is a gender like or maybe string value, then and if you don't want to drop it, then you know that normalization and standardization can only apply to numeric features. So in this list you don't include that string feature and include only numeric features, right? So that's why this kind of method is shown. But ultimately this has done the transformation, but the transformed data is at present just temporarily present in my environment. So I want to permanently assign it to these two columns, okay, feature 1 and feature 2. So now you can look at this, df feature 1 and feature 2 is equal to the scaled value of df feature 1 and feature 2, right? And now I again can look it, you can see this is okay because only head is shown 5 hmm, 5 observation top 5, but if I write df dot describe, then you will get the perfect idea that mean has become 0 and standard deviation has become 1. This mean is 6.666 10 raised to minus 18, so that is 0.00017 zeros and 10666, and similarly this is 0.00016 zeros and 111, so that is almost 0. This much also is coming because of floating point inaccuracy. Okay, and the standard deviation is 1.000, so that is nearly 1, and here also it is 1.000, right? So standard deviation is 1. Now let us see some differences between them. Standard scalar, this we have already done, but still once again, standard scalar adjusts the data to center around mean with standard deviation of 1. Okay. Then standardization does not bound value to a specific range, which also I told that which may be necessary for some algorithm that assume data is normally distributed, like SVM or logistic regression. So this is one thing which you must remember, that standard scaling, just like normalization, bounds all observation between 0 to 1, but standardization just symmetrically distributes the data points, and still it does not change the data distribution. That is again the beauty of it, but it does not bind between two fixed value like 0 to 1 or something. So values can be anything. Now there are certain algorithms like SVM or logistic regression which assume that the data is normally distributed. Normally distributed is that left side diagram here. So that is the data is bound between two specific points. Okay, so they may not work well if you do standardization. For them, normalization is itself required. Okay, these pre-processing techniques ensure that the data attributes have same scale. Even that I have explained, so I think it is fine. This avoids scenario where one features dominate over others, which also we have learned. Okay. There are some differences between normalization and standardization. One, normalization scales the model using minimum and maximum value. That is why normalization is itself called min-max scaling. And we learned its basic technique by definition using that table at the very beginning in that 7th chapter. This table. Okay, this is how you can do. So it is basically normalization is nothing but min-max scaling. Then features are on various scale. Normalization is functional. Here, standardization scales the model using mean and standard deviation. It does not bind along some definite maximum and minimum value, but it arranges the observations in terms of mean and standard deviation, so that finally data should have mean 0 and standard deviation 1. Normalization is useful when features are on various scale. Like we took the example of income between 25,000 to 85,000, while age or years of education, they were differing hardly by 6 or 12 or 15 units. So at that time, normalization is a fit technique. When variables mean and standard deviation both are set to 0, then standardization is beneficial. So that means when you want to set it to 0, then standardization is beneficial. That is when you want symmetric distribution, then standardization is beneficial. values are on the scale between 0 to 1 in normalization, or sometimes minus 1 to 1. So that is why normalization cannot manage outliers properly, because even the outliers will be brought in. That is why before doing normalization, I have included outlier removal in this chapter, because the order must be very clear. Otherwise, student knows everything, that whenever a new data comes, I have to do non-imputation, I have to do outlier removal, I have to do deduplication, I have to do normalization. But if you normalize in the beginning and then try to remove outliers, there won't be any outliers, because in the normalization everything has been brought between 0 to 1. Okay. Then in standardization, values on a scale are not constrained to a particular range, and therefore standardization is a better technique for managing outlier. So if you are going to do normalization, then outlier treatment should be done first and then normalization. If you are going to do standardization, then outlier treatment can be uh, done even after also. But still, it is a custom that outlier treatment is done first. Normalization is called scaling normalization, while standardization is called Z-score normalization. Whenever we will discuss about this Z-score, at that time you will learn the technique of this standardization also. Just like for normalization, we learn this technique, that from each observation, we subtract the minimum observation, right? And thereafter, we divide each of these xi minus x minimum by the range of the data, that is maximum minus minimum observation. And that values which are obtained, they are themselves called the normalized value, min max scaled values. Similarly, what is this z-score normalization? That we have not yet done, because what is z-score? That itself will be introduced in statistics somewhere in chapter 2021. Okay, but just remember that normalization, min max normalization, while standardization is called z-score normalization. Okay, then feature distribution is unclear, then normalization is helpful. Okay, and when algorithm is not making any assumption about the distribution of the data, then normalization is used. And many modern days algorithms like random forest or XGBoost, they are this kind of algorithm. They do not require specific type of data distribution, so normalization can be used. Okay, but if you are completely aware about feature distribution of your data, then standardization is better. And when algorithms create prediction about the data distribution, then standardization is applied. Now, what is the meaning of this last sentence? That becomes clear when we start making some project. But I will give you just a brief example. For example, suppose I am building a classification model for predicting heart attack probability. Okay, and the various features of that are BP, BMI, weight. BMI will include weight and height. So age, higher blood pressure, lower blood pressure, BMI, sugar level, whether the person has history of hypertension or not, whether there is a history of stroke or not, and all those things. Now, if that kind of heart attack prediction model is made, then clearly BMI will vary from 0 to 30. Sugar level can vary up to maybe around 80 to 400. In some extreme cases, it goes to 400 or say 300. Okay, and so scales are different. So you can do the standardization, but when you want to when you build your pickle model, and when you save your pickle model and finally build an app with user interface, in which end user will enter his blood pressure, enter his fasting blood glucose level and all that, then whatever values he is entering, they are again on different scale, right? They are glucose level, if he enters his my glucose level, suppose he enters that 180, and his age is maybe 45, and his BP, higher BP is say 140, and lower BP is say 90, and maybe I'm just deliberately speaking numbers which are for unhealthy person. Okay, while BMI is just suppose 30. So you can see the scales of the numbers are different. So if the input values which the user enters in the user interface directly go to the prediction model, then prediction model will not be able to accurately predict the probability of heart attack, because when that prediction model was being built, at that time only you scaled your data. So then whatever new data comes by user input, that also has to be scaled. Now you read this statement and you will understand. So we save not only pickle model, but we also save one scalar object, so that new data, whatever is entering into the from the user interface, that passes through that scalar pipeline, and thereafter scaled data that is fed to your pickle model. So then your pickle model will work perfectly well, because it was designed using scale data, right? So now you read this line and it will become clear. When any algorithm creates prediction about some data distribution or about some response variable, then standardization is applied once again. Okay, so you have to pass your data through that scaling pipeline also. Normalization is suitable when data distribution does not match Gaussian distribution. But if your data already have Gaussian distribution, then standardization is better. Now, many natural things have already nearly Gaussian distribution. For example, height of the human beings in a sample of maybe 100 persons almost varies like bell curve. Age of human beings, not age, sorry, weight of human beings almost varies like bell curve, like that. So then you can go for standardization. So again, here this is same thing written, that when to use normalization and when to use standardization. Suppose I need to constrain the data in a specific range, say 0 to 1 or -1 to 1. Clearly, normalization. When I want to maintain the original unit interpretation, so then again clearly normalization. Distribution of the data is not Gaussian. Here that we have done. Then again normalization. But we need to compare and analyze feature with different units and different scales. Now, suppose you want to compare maybe that example of heart attack prediction which I gave, that fasting blood glucose level, its scale is totally 80 to 400, while BMI, its scale is around 25 to maximum 40, 45. So in that case, they are totally different units, and their units are also different and scales are also different. Then better use standardization. You want to reduce the impact of outliers. As we here saw, that outlier detection, normalization is not helpful, because it will bring everything within this confined range, 0 to 1. So then even outliers will be brought to confined range. So they are not useful. But standardization can be used. It can manage outliers because it does not confine the data to some close bound. It just adjusts the data such that mean is 0 and standard deviation is 1. Okay. Normalization, its pros and cons are like this. Normalization brings fairness to your machine learning models and balance to your machine learning models. Now, these two words are very, very important, because when one practices machine learning in industry or real life, then many critics of the machine learning, they point out this thing, fairness. For example, at many airports in US or many Western countries, there are some automated AI models which check passengers' suspicious movement, and on the basis of that, they isolate that passenger and check that passenger in more thorough manner. They check the luggage of that passenger very thoroughly. They check the cloth and everything, what he's wearing, cap, whether he's hiding some weapon or not. Very so, because there are thousands of passengers moving over a big airport like maybe New York or Heathrow or somewhere, and you cannot manually deploy persons to check each and every person. So first you have to, from thousands of passengers, you have to isolate a few passengers who look suspicious, and for that AI, camera-based AI is used. But there, many people have alleged that as a suspicious passengers, mostly these AI models find the passengers such that out of 10, maybe 4 to 5 are black, and that is maybe 2 to 3 are Asians, while white people are less isolated as a suspicious. So then we say that the model which is detecting a suspicious passenger, that is not fair. Okay, and a lot of criticism occurs. But the solution of that is not to simply abandon that procedure and go back to manual. But the solution is that the data should be more balanced data, and it should be more representative data. It should cover all the cohorts, and then it should have equal distribution around white, Chinese, Asian, Indians, black people, so that better data will handle this. And of course, normalization handles fairness issue. Balance, there is something called bias and variance trade-off in data science, and we are going to see that in much detail, because it is one of the key concepts. But that is the balance. That balance is also ensured using normalization. Comparability. Suppose I have a data set, then it is not that you take the data set and do the null removal, do the deduplication, remove outliers and all those things, and straightway normalize and make the model by very first algorithm which comes in your mind. No, you have to try different algorithms, and at that time how to compare various different algorithms. So that comparability, and how to compare various features also which are on different scales, that comparability increases with normalization. Of course, it has this cone that there is loss of original value interpretation. Since everything comes between 0 to 1, what was original scale of one particular feature, that that is lost. However, that problem is not that big, because you can always save the original data frame as a backup, and you can look at the original data frame. And then one more limitation is that normalization is sensitive to outliers, which we have seen. Standardization, its pros is that interpretability greatly increases. Now, even this is very big thing when one practices machine learning in real life, because sometimes in machine learning models, particularly AI models, are criticized as black box model. Black box means, suppose they have isolated that suspicious passenger, but why this passenger is suspicious? That decision means, what are the factors which make him suspicious, and what are the factors which make another person non-suspicious? Earlier, the models were such that they were not interpretable, so they could not answer that. However, now after standardization, the interpretability of the model increases, and you will see that there are certain techniques like shape plots or other things by which you can even explain that this person is looking isolated as a suspicious person because of these factors. Okay, they also enhance comparability. Then they are useful for those algorithms which require normal distribution assumption, and they are robust to outliers. So standardization is robust to outliers. It also has that problem, loss of original unit interpretation, because it also changes each and every observation to rearrange them such that the mean is 0 and standard deviation is 1. and dependency on the normality assumption. So that means basic thing about standardization is that it assumes that your original data is normally distributed. Now, which out of two is more used? Then in practice, you will see that standardization is more used. Okay. Now these are the pros and cons in detail. So that I have already discussed this table. So you should read that. Okay. Now here, standardization use cases. This. So one use case is there is one important technique called principal component analysis. Now why that technique is so important? Because many times your data frame has several columns. Say this data frame only. Now this has income, age, distribution, gender, and there can be even more 5, 6 columns, say 10 columns, even 20 columns. Now suppose you are asked that represent this data diagrammatically. Now you are in catch because we cannot visualize anything more than three-dimensional. Even three-dimensional also diagram when you plot on the screen is two-dimensional, but somehow it manages to plot a three-dimensional screen by that oblong kind of view. So third dimension can be shown. But if there are 10 features and you are asked to represent that data graphically, then you cannot show it. Okay. So at that time, what we do is there is a technique called principal component analysis. There may be 10 features or 20 features or 30 features. It can divide, it can convert, transform your data into such manner that only two principal components remain. Or if you want to keep three, then only three principal components remain. So that is why it is called principal component analysis. So this multi-column data, say 20 columns are there, would be converted into two-column data. And then you can easily plot it. And still the message information which was conveyed by this multi-column data and the information which is conveyed by this two-column data, that remains the same. Okay. So this is a very important technique, very, very important technique, and it is used in finance, genetics, image recognition, etc. Okay. So that is the main use case of standardization. Before doing principal component analysis, you must standardize your features. If you have those 30 columns here or 20 columns and you want to reduce them to two-column data set, two principal features, please remember that you have to. And here there is no, you should, there is nothing optional. I'm saying you must standardize. Otherwise, your principal components will give completely misleading idea about your data. Okay. Then anomaly detection is another thing. Cyber security, fraud detection, quality control. So I said about anomaly detection, that credit card fraud detection example, which I have been repeatedly giving. Quality control also. For example, suppose there is a company which is making machine parts for the Boeing aircraft or Airbus aircraft, and it is a critical part. If that part fails, then there is a danger of air crash. Now that means that 100% perfection is required while making that part. And suppose it is coming out of furnace or whatever, it is a alloy, costly alloy, and out of 10 normal machine parts, for normal machine parts, what level of quality control is enough? Say you say that out of 100, if 99 are perfect machine parts and just one is wrong, 1% error, then it is acceptable. But if it is a machine part used for aircraft or something where accident means there is no chance of survival, so in those type of case, you impose stringent quality control. And at that time, even error of 1 in 10,000 machine parts is considered unacceptable. So maybe 1 in 10 lakh machine parts. So all those machine parts are passed through X-rays, and their X-ray images one by one is analyzed using computer vision algorithm. That is also machine learning important branch, right? So then anomaly or some crack, minor crack develops in only one single out of 10,000. So that also must be detected. So such anomaly detection is done using, for that first all features must be standardized. Okay. This is also one very important thing, one must remember thing, that what are the mistakes which people do before doing normalizing or standardizing. It becomes almost like a ritualistic process that as soon as data comes, start null imputation, then start removing outliers, start maybe removing single valued columns, then remove duplicate rows, then whatever other features, okay. But and then do standardization and move further in the data science life cycle. But you should ensure that when you do standardization, you standardize or normalize any one thing, training data and the test data separately. Now, what is this training data and test data? As such, I think we have done that discussion somewhere earlier. But here, after this process, next stage is model creation. And in model creation, what we do is, suppose I have a data set with 1,000 observations, then I divide my data set into 700 as the train observation and 300 as the test observation. Or I can use 800 as a train and 200 as a test. That is my choice. But then on the train observation, I train my machine learning model. But how accurate my model is, then that is to be tested on not the same data set on which it was trained, because the model has seen that data set. It might have remembered some of the data, some of the conclusions, some patterns. So we test the model on the remaining 200 or 300 observation which we kept separately as the test data, and which were to which the algorithm was not exposed during the training process. So entire training is done on 700 and testing is done on the remaining 300, right? So then in that kind of case, what happens is many people forget and they do normalization or standardization over entire data set in one go. That is before dividing in test and train data set. Okay. So at that time, the problem occurs is that the algorithm learns some things about the test data set which it should not learn, right? So because then otherwise how your test can be called honest? It is just like giving the question paper one day before to a student who is appearing for test. So if you give important IMP or some that these questions will come in your test, it is just like that, that your algorithm should not see the data, test data on which it is going to be tested. But if you do normalization or standardization on train and test data combined together, then you have missed the most important point. This point is called data leakage. Okay. And as a result of data leakage, what will happen is that your model will be overfitting. Now, overfitting means it will give excellent result on the trained data set or the given data set. But as soon as you try it on some unknown data set, unknown data points, its accuracy, etc., will fall like anything. From 90%, it may fall to simply 60% or 55% like that. Because on a new data set, it will be working on some patterns which it has not seen. While if you test it on the trained data set, it has already seen the entire trained data set because you by mistake did your standardization process or normalization process on entire data set. So please do standardization of training data separately and standardization of testing data separately. Okay. So two things are very important. One is preventing data leakage, and another is this in standardizing before doing PCA, principal component analysis. Then one more mistake is applying normalization and standardization on categorical variable. Now that we know that categorical variable, they are not standardized, only numerical variables are standardized. But many people do this, that they first encode the categorical variable and then standardize, but that is not required actually. For encode means what? Male and female gender is a categorical variable. Then you can choose some code like male is equal to 1 and gender is equal to, female is equal to 0. An entire gender column, maybe 10,000 observations. Wherever male, female are there, they will be replaced by 1, 0. So it looks that now it is a numerical data set and now I can do this normalization or standardization. No, it was originally a categorical variable. You encoded it just because machine learning models only understand numbers, but that does not mean that you should again normalize and standardize these data set. Okay, these columns. These columns are just better left as they are. Okay. Then ignoring the distribution assumption. So normalization wants the data to be lie in specific range, say 0 to 1, and standardization assumes that the data obeys Gaussian distribution. So you have to remember that, and that is why before doing this data pre-processing, we do exploratory data analysis. That is why this cycle is very thoughtfully designed. So data pre-processing, normalization, standardization, etc. comes here. But before that, we do that EDA, and in EDA only we plot the KDE plot, kernel density plot, which clearly will show whether the data obeys Gaussian distribution or whether it does not obey Gaussian distribution, right? Then there is this thing we have done, and normal distribution assumption, right? That is fine. We have done these use cases. And last problem is not considering outliers. So 4 problems may occur: data leakage, that is doing the standardization or normalization on entire data frame at once rather than doing on train set and test set separately. Then applying this, forgetting that these techniques are exclusively for numerical variable, which are right from the beginning numerical, not those which are categorical but encoded to numbers. Then ignoring the distribution assumption. If standardization requires Gaussian distribution, then it is okay, your data may not follow 100%